Hi there, I am Gekem Put. In this series on transverse pulses and waves, so far we have learned how to describe the motion of transverse pulses through a medium by examining both the motion of a crest through a medium and the motion of individual particles in the medium. In the next 3 lessons, we will identify and explain some very interesting properties of transverse pulses and waves. In this lesson, we will focus on what happens when there is a change in the medium through which a pulse is moving. By the end of this lesson, you should be able to describe and explain the refraction of a transverse pulse at a boundary, and describe and explain the reflection of a transverse pulse at different boundaries. This demonstration should give you a good idea of what reflection and refraction is. But it's important to note that you could also have only reflection or only refraction happening at a boundary. We are using 2 different slinky springs. On this side of the boundary, we have a slinky that has big coils. This slinky is light. But at the boundary, the medium changes. The coils of this slinky are smaller and the slinky is much heavier. When energy is transferred to the lighter slinky, a pulse starts to move through the medium. The velocity of the pulse does not change. We say that the pulse has a constant velocity. At the boundary, the velocity of the wave changes. The wave moving through the heavier slinky is moving much slower. We say that the wave has been refracted at the boundary. To explain this behavior, we need to look at the particles of the medium. The particles of the lighter slinky are represented by these small green spheres. These particles have a low density. The particles of the heavier slinky are represented by these purple spheres. They have a higher density because they have greater mass. To explain why the velocity changes at the boundary, we need to think of a relationship between mass and velocity. Can you remember a way of relating these 2 important quantities? Well, the equation to find the kinetic energy of any object is half the mass times the velocity squared. When energy is transferred to the medium, the particles of the medium gain kinetic energy. When the green particle is at the rest position, its velocity is a maximum, so its kinetic energy is a maximum in this position. Now, when the wave is refracted at the boundary, the exact amount of kinetic energy must be transferred to the heavier purple particle, according to the law of conservation of energy. Remember, energy cannot be created or destroyed. So the purple particle can never suddenly have more energy than the green particle. Now look carefully at the equation for kinetic energy. Do you see that because the purple particle has a larger mass, we will have to multiply the mass with a smaller value of velocity squared to ensure that the kinetic energy of the purple particle is equal to the kinetic energy of the green particle. So the purple particle must move slower. By applying the law of conservation of energy, we can explain why the velocity of a wave changes when it crosses the boundary between 2 mediums. Can you predict what would happen if the wave moved in an opposite direction? That is, if it moved from a more dense medium into a less dense medium. Have a look at what happens and see if this confirms your prediction. Here the pulse starts in the heavier slinky and moves into the lighter slinky. Look, the wave speeds up when moving from the heavier slinky into the lighter slinky. Now, what do you think would happen when the medium at the boundary is made up of particles that are so heavy that the energy of the pulse is not enough to move the particles of the second medium? Well, we know that the pulse cannot just stop because energy cannot be destroyed and must be conserved. So, at a fixed boundary, a pulse or wave will be reflected. Let's investigate what happens when half a pulse, in other words, just a crest, is reflected at a fixed boundary. Firstly, you should notice that the direction of the pulse changes at the boundary. Secondly, you should find that if you compare the pulse length before it is reflected and after it is reflected, the pulse length does not change. The period of one cycle is also the same before and after reflection. Remember, these two quantities can be used to calculate the wave speed by using the equation v equals lambda divided by period. So we can conclude that the speed of the pulse does not change during reflection. But there's another very important thing to notice. Notice the pulse has a crest above the rest position as it moves towards the boundary. We call this pulse the incident pulse. After the pulse has been reflected, it is called the reflected pulse. Notice that this reflected pulse has changed direction and forms below the rest position. We say the crest has been inverted during reflection. Before we explain why transverse pulses are inverted during reflection, we need to understand a very important law that applies to forces. Sir Isaac Newton investigated motion and described the relationship between forces and motion very clearly in three important laws. For this lesson, we need to look at Newton's third law of motion. He stated that when body A exerts a force on body B will exert a force on body A that is equal in magnitude but opposite in direction. These pairs of forces have become known as action and reaction pairs. Here is an interesting example to explain this concept more clearly. This plastic cold drink bottle has been filled with a mixture of hydrogen and oxygen gas. When the gas is ignited, a chemical reaction takes place. The bottle pushes the hot expanding gases out of the cold drink bottle. The gases exert a reaction force on the bottle, pushing the bottle forwards. The reaction force is equal in magnitude but opposite in direction to the original action force that the bottle exerted on the gases. We can now use this law to explain why pulses that are reflected at a fixed end are inverted. Have a look at the motion of particles in the medium. When a half pulse moves through the medium, energy is transferred from one particle to the next. The first particle is pulled upwards by the disturbance. The second particle is pulled along by the movement of the first particle. But the second particle exerts a downward force on the first particle, causing it to slow down. This means that each particle of the medium experiences an upward force that causes it to move from the rest position, but there's also an opposite force causing the particles to slow down. This opposite force means that particles reach their maximum displacement with zero velocity. They then change the direction of motion and return to the rest position. Now, when the last particle of the medium starts to move up, an upward force is exerted on the fixed end. The fixed end cannot move but still exerts a downward force on the particles of the medium. This downward force causes the particles to move below the rest position. The result is that the pulse is inverted and reflected by the fixed end. Now, reflection does not only take place in strings and springs. There are in fact many examples of reflection you can look out for. Ripples traveling through a swimming pool are reflected when they hit the side of the pool. And we know that if you shout loudly in a cave or a large building, you will hear the sound reflecting as an echo. Light shining onto a mirror is another example of reflection. We will study this example in more detail in the series called Geometrical Optics. Now look at this rhythmic gymnast. The pulses she's generating in the ribbon is being reflected when the end of the ribbon is fixed. But what happens when the end of the ribbon is free to move? Do you think there'll be any evidence of reflection if the end of the ribbon is not attached to any other medium? Let's watch the pulse as it moves towards the loose end of the ribbon again. Do you see that the pulse actually moves back through the ribbon? This must mean that the pulse is being reflected. The reflected pulse has the same wavelength and speed as the incident pulse. But look carefully, the pulse is not inverted from the free end. Once again, we can explain this behavior by looking at the motion of the particles of the medium. When the last particle of the medium experiences an upward force, this particle accelerates upwards. Because the end is not fixed but free, there is no downward force on this particle. This particle does not stop at the same position as the other particles. Its displacement from the rest position is greater than the amplitude of the pulse. The last particle pulls the particle next to it upwards too, but then this adjacent particle pulls the last particle down. And this generates a reflected pulse that is not inverted. For your task today, I want you to analyze two velocity time graphs that describe the motion of a transverse pulse at a boundary. Identify which graph represents reflection and explain why you have made this choice. Identify which graph represents refraction at the boundary. Explain how the medium changes. I hope you have fun with this task. Now, reflection and refraction are not the only interesting properties of pulses and waves. So be sure to join me for our next lesson, where we will explore what happens when two pulses interact with each other in the same medium. Goodbye.
Yeah.